Hello friends, welcome to the next video which is on file structure indexing. Hope you like my previous video which was on semaphore. I got few queries on that also. I will try to respond that too. So today what I am going to discuss is again one of the important topic for I can say GATE 2015, and I am expecting a question on this. As I have written, it's having a weightage of 2 to 3 marks. You can just scan through all the previous year paper and you will find that definitely one question is there. So now what actually we are having is database and a secondary storage. As you all know, database will be stored in some secondary storage, and database will be having records. Okay, so a table will be divided into records, and we are assuming a secondary storage to be divided into blocks. So now each record will be stored into some block, assuming that your block size is 512 bytes and your record size is 100 bytes. So tell me how many records you can store in one block. Again you will ask how to store it. Okay, so for that there are two things, and what we are assuming is there are total 500 records. So to store this 500 records into this block, we are having two methods which I call it as spanned storage or spanned organization and unspanned organization. Now what is spanned organization? Spanned organization is something where taking the current data, see each record is of 100 bytes and total this, if I am considering this is to be a 512 byte block, so that means this is my first 100 byte record, this is the second, third, fourth, fifth 100 byte record, and now only 12 byte is remaining. In a spanned organization, what it will do is it will consume this 12 byte and it will continue with the second block. Okay, so in your second block actually one record requires 100 bytes, so 12 bytes are already consumed, so remaining 88 bytes will be available over here. Then 100 byte, 100 byte, 100 byte, and so on. So again whatever space will be remaining will be again consumed to store one record, and then again we will take to go move to the next block. Now what happens in unspanned organization? In unspanned, the remaining space, that was, let's say again the same data, 100 byte, 100 byte, third record of 100 byte, fourth record of 100 byte, and the fifth record of 100 byte will be there, and that out of that 500 bytes have gone, so those 12 bytes will be discarded, nothing will be stored over here. So I can say in unspanned only 5 records per block are stored, whereas in spanned organization how many records you require or how many blocks you require, as we saw that the total there are 500 records, okay, and that I need to store into 512 bytes. So 500 into 100 is the total size of the records. This, if I am dividing it by 512, will give me approximately 98 blocks, whereas over here I will require total there are 500 records. Okay, so 500 divided by 5 will give me 100 blocks. So this is ideally the difference between the spanned organization and an unspanned organization. Moving ahead, what do you think is the time requirement? Say if in your spanned organization, what is required? What time is required in spanned and unspanned organization? It is very clear that spanned organization requires more time to access because of this 12 byte. 12 byte, then the next pointer will be pointing to this 88 byte. So this is like a record is divided, it is split into two portions. So I require more access time, whereas in unspanned organization, the time requirement is less. So the question is, what is indexing and how can we solve this? So we can solve this using a concept of indexing. So what is indexing and why we require index? So indexing, it is ideally, I can say, to make search faster. Okay, Now assume you are having 100 records and you are performing linear search on it. What time it will require? You are taking 100 records are there, 100 records are loaded into main memory, then you are searching it, and then again you are unloading those 100 records. That means almost 200 times we are access, 200 times it is consuming. But if I want to make the search faster, I need to think something else, and that is indexing. So indexing is ideally which will make your search faster. For each record, we will have a pointer, or I can say a index. Okay, so what concept we are building over here is, I can say I am having an index which points to a record pointer, or I can say a record, and this is stored in our secondary storage. And what is in secondary storage? Those are the blocks. Okay, so we are having an index which is pointing to the record pointer, and this records are stored into the secondary storage, which are blocks. So ideally we create a combination of index and the record pointer, and this index and record pointer combine to create one index file. Getting this point? That for each record, whatever records we are having one index for it, and index and a record pointer together form a index file. So you must be knowing two best data structures in tree, that are Btree and B+Tree. So in GATE there are questions on Btree and B+Tree, or maybe majority time on B+Tree. So we will see what a Btree and a B+Tree is. Btree. Btree is a data structure in which data is stored at an internal level, internal node, as well as in the leaf node. So I can say that if this is the root, and if I am considering order, okay, so degree, what is degree of a tree? If let's say degree is equal to 3, okay, so what is degree? Degree is the maximum number of child pointer that can come in a particular block. So if degree is 3, that means I can have only 2 key values. So let's say these are the 2 key values. Again I am having degree 3. So this structure is a Btree structure, where if I consider this as my leaf node, then I can have only 2 key value stored in each block. So your data is stored in this as well as this. So everywhere data is stored. So the point is, what will be the general structure? Okay, now if there is a data, let's say I am having some data B over here. So B will have some pointer towards left side, which will be pointing to the record. See, B is nothing. If I am performing some indexing should be on some key value. Okay, you must have seen in your computer also that whenever you are searching for something, it suggests, my Windows Explorer is suggesting, do you want to index this file for searching faster? And if we click yes, then it is performing some indexing. So indexing generally is always on a key value, and that is a primary key. Okay, in case if you are not doing on a primary key, you can go on a secondary key. Again, it's again a different topic. So now if you are coming back to this, that for each key value I will be having some pointers. So I can define a general structure like this: a pointer 0, key 1, pointer 1, key 2, pointer 2, up to pointer n, kn, and above, before it will be pointer n-1 and kn-1. Okay, so from this I can identify that if there are n pointers, okay, so this will have n pointers. Can I say it's a child pointer? Yes, these are the child pointers. These pointers are child pointers. And being like it's a similar structure for all the internal node as well as the leaf node, I can also say these are the block pointers. So both are same in Btree. And see, K1, K2 up to n minus 1 and n. So overall I can say if I am considering to be n minus 1 also, it will be 1 key less, as we have seen over here. If degree is 3, I can store only 2 key values. So there will be n minus 1 key values. Okay, so getting this point, where in Btree for a particular node you will be having n pointers, which are your child pointer or block pointer, and there will be n minus 1 key values. So now the question comes, what is this structure? This is nothing but is your one block. So whatever block size is given, this is to be considered a complete block which can store all these values. Okay, so the question is how many values we can store and this and that. So based on some data we can calculate it. So next we will be taking one example on this block structure. So for a B-tree, if I am having a degree n, so I can say it will have n minus 1 keys, n minus 1 record pointer and n child pointer. So that is what I have drawn over here. This is your complete block where I am having P0, P1, P2 up to Pn, this many number of record pointers, or I can say block pointers. For each key value I am having a record pointer. Now what is this key? Key is nothing but I am finding an index. Okay, at that particular point I will start searching. So for this k, my records will start from R1. For k2 it will start from R2. Now if I want to find out for the given, let's say you know the size of P0, you know size of k1, you know the size of R, and you want to know what is the degree of this equation, or what is the degree of a particular node, then I can use this, that given if block size is B bytes, key size is k bytes, and record pointer is R bytes, then what is the total block size? So from the figure, what I identify, that your total block size, there are n minus 1 key records and record pointer. Okay, so I can say n minus 1 into k plus n minus 1 into R plus how many block pointers are there? Total n block pointers. So n into b. So this equation will give you whatever value you want to find. See, if there are, how many unknowns I am having? 1, 2, 3, 4 and 5. 5 unknowns. Out of 5, only 4 are given. Definitely you can find the fifth one. So generally you are asked to find out the degree of a B-tree or for a particular node. So I will give you one example on this and we'll solve it, and then we'll move to the next topic of B+Tree. So the question is, let the size of the block pointer be 8 bytes, key size be 4 bytes, and record pointer be 6 bytes. And given that the block size is 512 bytes, what is the maximum possible degree for the B-tree? So what should be the solution now? We are having the formula, we can use directly the formula, that is n minus 1 into key size plus n minus 1 into record size plus n into the block pointer will be equal to your block size. So what we are supposed to find? We are supposed to find n. Okay, now k. What is k? That is your key. So this implies n minus 1 into what is your key size? 4 plus n minus 1 into what is our record size? So record size is 6 bytes plus n into block size of 8 bytes is equal to 512 bytes. This you can solve it. It's like 4n minus 4 plus 6n minus 6 plus 8n is equal to 512 bytes. This implies 4 and 6, 10, 10 and 18. 18, 10 is equal to 522 bytes. Is it 18? 6 and 4. Yes, 18. So that is n is equal to 522 over 18, which will give you somewhere around 29. Now suppose say it is, we are asked to find maximum, okay, and suppose you are getting a decimal value, what you will do? You will take the floor function. You will take the floor function because that is the maximum thing which you can accommodate. So I can say in general this is your answer. So the maximum possible degree of a B-tree is 29. Now what we were having, let's say there are 1000 records. So here is some magic. There are 1000 records, okay, and I am using B-tree for indexing this. So 1000 records, and I know that the degree is 29. So how many blocks I require? That is log 1000 to the base 29, which will give me somewhat, if I take the ceiling function, it will give me 2. So that means only 2 block access are required. So 2 block access compared to linear search. So in linear search, how many block access? As we know that there are 512. 512 is your block size and record pointer is 6. So 512 divided by 6, it will give me somewhat around 85 blocks. Okay, so 1000 by 85 is somewhat around 12 block access. Now just compare where 12 stands and 2 stands. So definitely Btree is very faster than your linear search. So I can say we can use Btree, but again I am having more efficient thing than this, that is B+Tree. There are pros and cons in Btree and B+Tree, but definitely we need to know both. So next topic is B+Tree. You must be knowing the difference between Btree and a B+Tree. In B+Tree, your internal nodes is only used for indexing. Okay, you cannot store the data. Whereas your leaf node, so assuming that these are the leaf nodes, will have data as well as the record pointer. Okay, plus these nodes are connected. Okay, this is a linked list. I can say if there are 2 records, then this record this will be in ascending order. So that is A, B, C, D, and so on. And definitely I will have a repetition of A over here. And if from this side, if it is, let's say, E, then I may have E over here. So this portion, all the internal nodes are only used for indexing, whereas your leaf node will be used for storing the key as well as the record pointer. So now we need to see what will be the structure, what will be the internal node structure. So if I take the leaf node, okay, so assume that this is your complete block. Okay, so this is my block. In this block, I am having the pairs of K1R1, K2R2 up to Kn Rn, and a pointer pointing to the next leaf node. Now what will be the order of the leaf node? It is the maximum possible number of pairs you can store in this plus the block pointer. So what should be the equation? The equation becomes block size is equal to n into k plus n into r plus 1 block. Okay, remember there is only 1 block pointer, so plus b. This can also be written as n into k plus r plus b. So clear? For a leaf node, what can be the maximum order, or how you can determine? Using this formula, where for a given block there will be n pairs, that is the maximum number of pairs of key and a record. Now what for an internal node? What you can have for internal node? In internal node, we'll have only the pointers. Okay, so that will be the block pointers that are used for indexing. So this is again your block, and if I'm dividing it into the pointers, so I'll have P0, K1, P1, K2, P2 up to this is Pn, this is Kn. Okay, so how many key values are there for indexing? Those are n minus 1 into k plus n into b. These are the block pointers, and this will give you the block size. So clear? Again I am repeating, for internal node the block size will be n minus 1 times k plus n times b. Why n minus 1? Because it is the degree. If degree is n, you can store only k key values, and n indicates the number of child pointer. So for internal node, this is the equation, and again I am writing for the leaf node. For the leaf node, the block size will be n into k plus r plus b. So using these two equations, we can identify the maximum possible order or the block size or whatever the question is. So next I will take a gate question for this, finding out the block size for a leaf node. GATE 2007 question taken by IIT Kanpur. What is given? The order of the leaf node in a B tree is the maximum number of value data record pointer pairs it can hold. So it is already given that this is what a leaf node can hold. Given that the block size is 1 kilobyte, data record is 7 bytes, value field is 9 bytes, and block pointer is 6 bytes. What is the order of the leaf node? So do you feel, is it simple now? What is the solution? The solution is, we know the formula, block size is equal to n times k plus r plus b. Now what is the block size? It is 1020, 1k. 1k is 1024. So 1024 bytes is equal to n into key. Key is the key value. So it is, we are given some value pointer. Okay, so value field is of 9 bytes plus the record, that is 7 bytes, plus b, that is 6. So this will give me 9 plus 7, 16n plus 6 is equal to 1024 bytes. Therefore 16n is equal to 1018. So n is equal to 1018 over 16, and this will give me 63.25 something, and I will take the floor function, which is 63. And if you go by the option, this is option A, option B is 64. So make sure that you are not taking this as n minus 1. Okay, many of the textbooks you will find, or many of the PPTs you will find n minus 1, but it is not. It is the maximum possible pairs you can store. So I always need to take n, and I will get 63 as the answer. Hope this is clear. I will give one more example for GATE 2004. GATE 2004 question, the order of an internal node is given, which is having the maximum number of children it can have. Suppose that the child pointer takes 6 bytes, search field takes 14 bytes, and the block size is 512 bytes. You are asked to find what is the internal node. So now the solution, we can directly use the formula. What is the formula? Block size is equal to n minus 1 times your key value plus n times your block value. So your key value is nothing but your search field value, and b is the block pointer. So 512 bytes is equal to n minus 1 times 14 plus n times 6, which is 14n minus 14 plus n times 6, so that is 20n, and this becomes 526 bytes. Therefore n is equal to 526 by 20, and again you will take the float function, you will get 26. So this is what the order, the maximum possible order for an internal node. See how simple it is. Simply if you know the formula, 2 marks is in your pocket, nothing to lose over here. Again, don't make any mistake in identifying the child pointer, the search field value. The words may be different, but concepts remain the same. Hope you like this video.